Hey everybody, it's Jay from Norman S. Wright. In last week's video, I talked about how a CFM was a CFM at all altitudes and temperatures, but how the heat transfer capacity changed with air density. So let's talk about that a little bit more. I want to talk about how it affects water coil sizing. So let's get started. First, a refresher on why altitude matters. At high elevations, the air pressure drops and the air becomes less dense. This means for every cubic foot of air, there are simply fewer air molecules. Since heat transfer depends on how many molecules of air can pick up energy from the coil surface, less dense air won't absorb as much heat. So let's move this up. The difference in air density doesn't change the CFM value itself. 1,000 CFM at sea level is still 1,000 CFM in the mountains, but the heat transfer potential of that air is lower. That's why it's critical to account for altitude when sizing water coils, because if you only use the standard air cataloged data for coils used at altitude, your system will underperform. So at altitude, where the air density is lower than standard air, the heat transferability of the air will be reduced. Let's move this over. When you select water coils in a selection program, you enter the CFM and altitude and enter an air temperature. The calculation isn't just using the CFM for its calculations. It's really looking for pounds per hour passing over the coil, called the mass flow rate. To get this, it converts CFM to pounds per hour, where the mass flow rate, m, equals density times the face area of the coil times the velocity of the air moving over the coil face. So m equals rho times A times V. And then to calculate the heat transferred to the air from the coil, Q equals m times delta H, which is the change in enthalpy. Let's scoot this up a little bit. Usually if you don't change anything, it's going to use standard air at sea level and 70 degrees Fahrenheit to get the density. The density for standard air is 0.075 pounds per cubic foot. So let's compare that to if you are at an altitude around 4,000 feet, where the air density is about 0.065 pounds per cubic foot. So Q equals m times delta H, which is equal to rho times A times V times delta H. So for standard air, it's 0.075 times A times V times delta H. And for our air at altitude, Q sub A, is 0.065 times A times V times delta H. Now, without putting any other actual numbers in here, if everything else is equal, you can tell that Q sub S is going to be greater than Q sub A. So at altitude, you will get less heat transfer through the same coil at any given CFM. So let's scoot this up again. So to get the same heat transfer at altitude, you'll either need to increase your CFM, which increases your velocity and puts more air over the coil per minute, or increase your coil size, which increases the face area, so you have more coil area to transfer the heat over. So let's bring everything back on screen. As a general rule, you get about a 3% reduction in capacity for every 1,000 feet in altitude increase. So that's how altitude affects water coil selections. Don't forget to like and subscribe to our YouTube channel. Thanks for watching, and I'll see you next week.